Hello, in this video we'll show how to build a vehicle with multiple wheel axles and how to model generic moving part using rigid body constraints. There are countless multiple axle vehicle configurations, so instead of trying to cover all of them, we'll look at 3 examples. Each demonstrate a different drivetrain and axle arrangement. Preparing a vehicle mesh in Blender or 3ds Max can take some time, especially if you are new to the asset tool. To keep this tutorial focused, we already prepared the mesh, imported the FBX file, and authored the basic physics. If you like to learn that workflow, watch the previous tutorial or download the SDK and experiment with the included demos. If you enjoyed these videos, please like us and subscribe. It already helped the channel. We start by loading a medium-duty flatbed tow truck into the asset tool. Before adding any physics, we verify that the collision shapes are correct and that every wheel is oriented properly. If something looks incorrect, it's much easier to fix it at this point in Blender than later. Once everything looks good, we can build the drivetrain. The tow truck is powered only through its 2 real axles. To model that, we create one differential for each real axle, then connect both of those to a parent differential. Then we add the engine node. The default settings of a motor are intended as general purpose values. Since this truck uses a diesel engine, we reset some parameters like lowering maximum RPM and increasing the available torque at any given RPM. If you have real engine specification, you can enter those directly after converting them to the metric system, but for this demo, we'll simply use reasonable values. You now proceed to build the drivetrain that connect the wheels to the motor using looping joints. Starting at the rear, we connect each wheel to its axle differential with a loop joint. Then we connect both axle differential to the parent differential, and finally we connect the engine to the transmission. With the connections in place, you move to configure each loop joint. Every wheel to differential connection is changed to a multi-body differential axle. This joint combines and distributes angular velocity between the connected shafts. To make it work properly, one of the child frames must be rotated 180 degrees around the x-axis. The connection between axle differential and the parent differential use the same joint type and the same orientation rule. Finally, the connection between the engine and the last differential is set to a multi-body vehicle gearbox. A gearbox have several parameters: number of gears, gear ratio, clutch torque and losses, crown gear, and reverse gear. For this example, most parameters seems right. You can always tweak them after experimentation, or even better, you can enter real world values should you have them. For now, we only change the ground gear sign. Now let us configure the vehicle map. You first inspect each body part and verify that its local center of mass is reasonable. On this model, the bed is split into two separate pieces. This may skew too much the weight height of the complete vehicle. So we lower the center of mass of each of the offender part. Also, in a real vehicle, the bed is made of solid steel but has a smaller volume compared to the chassis. So to represent that, you enlarge the relative mass of the bed pieces. Once that's done, you run the normalize mass distribution tool from the main menu and enter the vehicle total weight in kilograms. You click execute. The tool will calculate a mass distribution. After that, you can check that the actual calculated mass of each body part seems right. If it doesn't, you can simply reduce or enlarge that part weight influence and execute the tool again. You can do this until the overall model looks correct. You should now have a fully drivable vehicle, but you still want to add some specific vehicle functionality. A flatbed tow truck has two moving components, a tilting bed and a sliding platform. The tilting bed will be represented by a hinge joint configured as a proportional derivative controller. The sliding platform will be represented by a sliding joint also with a proportional derivative controller. These are both a one-dimensional degree of freedom joints. Each will be controlled by a custom property that specifies the rate and the limits of the independent joint variable. With that, you should have a complete tow truck model. Save the model and move to the application for testing. Inside the application, verify the vehicle basic functionality. Start by confirming that the engine behaves like a proper diesel engine with adequate RPM responses. Verify steering angle and steering rate. Test both the tilting bed and the sliding platform. Check the gearbox, park, neutral, reverse, and the 4 gears. You can think of this check as a smoke test. If they all pass, you are now ready to test drive the model and verify the handling. Drive over obstacle and confirm that its interaction with the environment behave plausible or realistic. In the next section, we will use this design as the foundation for 2 additional heavy vehicles. Although the overall workflow remains nearly identical, different parameter choices produce very different driving characteristics. Until then, thanks for watching.